he's going to speak about A-expansions of vectorial Drinfeld modular form. So.
Thank you. Well, let me first thank the organizers and say that I'm still a postdoc, so maybe a professor soon, a couple of years. And yes, I do come from the Middle East, so Texas A&M, Qatar, not from College Station or any other campus in the US. Now, today I want to talk to you about A-expansions, and towards the end I'll talk to you about A-expansions of vectorial Drinfeld modular forms. So let me fix some notation first. A is going to be FQT, K is going to be the fraction field, and A plus is going to be the set of monic polynomials in A. K infinity is going to be the completion of FQT at infinity, or FQ and then Laurent series in 1 over T, and C infinity is going to be the completion of a fixed algebraic closure of K infinity. So I'm sure everybody here is familiar with this. This is the usual analogy with Z, Q, R, and C, although, as you know, sometimes it's not a very good analogy because C infinity is quite a lot bigger than the complex numbers. Okay, MKM is going to be the space of Drinfeld modular forms for GO2A. So in this talk, I'll mostly be concerned with GO2. I think I'll mention gamma naught and gamma 1T at some point, but if I don't specify the group is always going to be GO2. And SKM is going to be the cuspidal forms. K is the weight, M is the type, by the way. Now, I want to define U, so this is a function. It's 1 over the Carlitz exponential, and then it's rationalized in some way. And U sub A is going to be U, and I plug in A inside A of Z. And A is an element in the monics. P is going to be either a prime or the irreducible that generates that prime. And Gn, so let me define what Gn is, because I'm almost sure that I'm almost sure that some people would not know what this is. So imagine that I take the following: 1 over x plus sum over lambda is in pi infinity a lambda. Okay, so this is a bad choice. Z here. Okay. And I compared this with the sum, lambda again in pi tilde a, 1z plus lambda to the n, okay? Now, it turns out that there is a polynomial, g sub n, such that if I plug this guy in, I get exactly this guy. Okay, so this is g sub n. It's a polynomial of degree n. And I'm going to take it normalized so that it has 1 as the first non-zero coefficient. So in general, the degree is n, but it's sort of difficult to know what the first coefficient is, which is the first non-zero coefficient. Except in the range up to q, it's always x to the n. So this is something that I would use. Now u sub a, remember u sub a was the thing that I defined before. U sub a is u of az. It turns out that u sub a is actually a power series in u. So it starts out as u to the q degree of a. Okay. All right. So when I say f is a Drinfeld modular form of weight k and type m, I'm always going to think about f as being given by a power series in u. So u plays the role of q for classical modular forms. It's a bit different because the series that I have written down right here only converges for some z, not for oz, but the Drinfeld upper half plane is connected, so even though we don't have convergence everywhere, the series on the right always determines f uniquely. Okay? So I'm always going to think of f, because of this, as given to me by this Fourier type expansion. Okay. Now we have Hecke operators. So T sub p for p a prime, and the formula for them is given on this slide. Unlike the classical case, the Hecke operators are completely multiplicative. So T sub p times T sub q is the same as T sub p times q, regardless of whether p and q share factors or not. Okay, so to define the Hecke action, it suffices to look at just the primes. And not give you any more formulas, I should say, because of this complete multiplicativity. And T sub p is again a linear operator, and it preserves cuspidality, and unlike the classical case, it also preserves double cuspidality. Okay, and cuspidality just means, as usual, that the zeroth coefficient is 0, and double cuspidality means the zeroth and the first are both 0. All right, so here's what I want to do. I want to investigate the relationship between the Fourier coefficients of a modular form and the Fourier coefficients of the modular form when I act by the p-th Hecke operator. Okay, in particular, I want to see if f is an eigenform for all of the Hecke operators. Then I want to know how is this affected on the Fourier coefficients. And such relation is well known classically, right? So if you normalize, if you're talking about SO2, if you normalize your eigenform, it's always a new form because you're dealing with the full level, and the p-th coefficient is equal to the p-th eigenvalue. Okay, now this appears to be difficult. So there is a formula with which you can compute the Hecke action, but you sort of have to do it prime by prime. So if you give me a prime, maybe not of a very high degree, maybe of degree 4 or 5 is the maximum I can do, then I can compute the action. However, I cannot give you a receipt for what the coefficients are going to look like. And also, there is something else which is different than the classical case. So here, the Hecke operators are indexed by the monic polynomials, and my Fourier coefficients are indexed by the natural numbers, right? And in the classical case, those two things match because the monic polynomials, or the primes, they are, again, sort of indexed by z. So it's perhaps better to look at some sort of an A-expansion, and not the Fourier expansion that I showed you before. Okay, well, before we get to that, maybe we should look at some examples, because I didn't just write down what A-expansion should be. I sort of looked at examples that were already out there. So first off, we have Eisenstein series. So here K is congruent to 0 mod Q minus 1. Otherwise, this E sub K can still be defined by the 0. Then you see that E sub K, which is defined by the usual formula for Eisenstein series. So here A and B are in A. Okay, or well, let me take A and B to be in pi tilde A. So okay, and pi tilde is the analog of 2 pi I. So then this looks like it has an A expansion. There is a coefficient C sub 0 K, and then afterwards you have fixed K already, and you have an expansion in terms of those GK of UA. And this was known to Gauss when he first studied those, and it was known to him that these are eigenforms and the eigensystem is p to the k. So the p-th eigenvalue is p to the k. Okay. Now here are two more examples. H and delta. So actually H and delta were already discovered before 2011. So maybe this here is misleading. So H and delta were discovered by Gauss and Gekeler, and they didn't know that they were eigenforms with eigensystem P for H and eigensystem P to the Q minus 1 for delta. And in 2011, Lopez showed that they also have A expansions. So there is this funny expansion for H. A runs through the monics, and then the expansion is A to the Q UA, and then for delta, it's A to the Q minus 1 UA of Q minus 1. Okay? So maybe with armed with all of these examples, we have to study expansions that look like this. So I'm going to take a modular form, I'm going to fix n, which I'm going to call the exponent, and I would like to know when I can write down f as an A expansion in Gn of ua. Okay? So C sub 0 of f is the zeroth coefficient in this expansion, and C sub a of f is the 8th coefficient in this expansion. Okay? And if you write things down, you immediately get that if C sub 0 is 0, then this is if and only if, then your function is cuspidal, and it's also not very difficult to see that n has to be congruent to the type modulo q minus 1. Okay? Well, there are several questions that you can ask. What about uniqueness? I mean, usually when I come here and I say, well, we have a Fourier expansion, you think that the coefficients give you the expansion and vice versa. Well, it turns out that if we fix n, okay, so again we fix n, the exponent, then if f is equal to g, then the coefficients are the same. Okay. Well, convergence may be another thing that we have to worry about. Well, here, if the absolute value of C sub a of the 8th coefficient has polynomial growth in A, then the expansion converges. Then the Hecke action, which is really why we want to consider this, well, if you can see, this is a really nice formula. Right? So if you see, we have we have shifted our expansion by PA here, and then we have the same coefficient as the one in A, multiplied by p to the k, and here we haven't shifted anything, but we're only taking things which are relatively prime to p. Okay? So this gives us a lot of hope. And in fact, if you use this, you immediately get the following. Well, if I have f, an eigenform, and if this f has an A expansion with exponent n, then the eigenvalues have to be p to the n. Okay? The 8th coefficient has to be a to the k minus n times the first one. Okay? And in particular, you get some sort of a multiplicity 1 result. Right? So the multiplicity 1 result here says the following: if you fix k, which is the weight, and if you fix the eigensystem, which is this p to the n, and if you have an A expansion, I mean this is also important, then, let me get this away. No. No. Right, okay. Then f is uniquely determined by its weight and eigensystem because it must look like this. Right? Okay. So all of these things were well known before I did anything in mathematics. I'm not sure if they have appeared anywhere, so I did put them in my paper, but all of them were known. However, what I proved is that there are more examples. Okay, so this was my PhD work. So my theorem is the following: let k and n be two positive integers, such that k minus 2n is a positive multiple of q minus 1, and then n is less than or equal to p to the valuation at p of k minus n. Okay, and here p is the characteristic, by the way. Then this funny-looking function f kn, which is defined by the expansion on the right, is actually a Drinfeld modular form, and it's a cuspidal Drinfeld modular form. And the condition that n has to be less than or equal to p to whatever power it is equivalent to the condition that n and k share the same p digits up to log p of n. Okay. Now, a couple of things to notice. This is an infinite family of things. Okay, so now there are infinitely many examples of cuspidal eigenforms with eigensystem p to the n that we have. Okay, which I think was not the case before. And here are some examples. Well, one family that definitely satisfies all the conditions is if I take a to the q to the n as my coefficients. Okay. Another family is if I do this with 2 q to the n and then I don't use the first Gauss polynomial now, but the second one. Okay, and then maybe just a random example. It's for a q equal to 3. There's this this function in S42, 1.
May I simply ask something?
Sure.
So the second example, is it the square of the first one?
I suspect so, but I'm not sure. Yes, I suspect, in fact, if I put j instead of 2 there, and j is less than or equal to q, yes, then it's the jth power of the first one.
Because you have the same phenomenon comparing h and delta.
Yes, yes. So in fact, for h and delta, I can prove this, and for h up until h to the q, I can prove this because the space is small. So I can simply compare, because I know that both things live in the same space. But for these guys, I cannot do this.
But there are some other examples of modular forms in these spaces with these parameters, which have some arithmetical significance. We can try to compare them with your whether you have found expansions of some known forms.
Sure. I mean, one thing which is good is h and delta have those expansions, and g has this expansion. So these are the basic ones. One thing which is bad is that products sometimes work, sometimes don't work.
For instance, one candidate for that first form would be the derivative, the derivative of the Eisenstein series of the corresponding weight.
So take Eisenstein series of weight q to the n minus 1 or something. Maybe.
Q plus n minus 1.
Q plus.
And then the third derivative shifts the weight by 2 and the type by 1. So it would be just right there.
Yes. I'm not sure, but we can try this. I mean, I have a formula for I have a recursive formula for actually the first family, which I don't have in the slides, but I have in my paper, so we can take a look later.
Sorry for interrupting.
No. By all means, you should ask, interrupt me, and things like that. I mean, it is a talk. I'll ask you questions at the end, by the way. So I'll interrupt you. So you shouldn't feel bad interrupting me. Okay, so here are some examples, some families, and some examples that I just picked before the talk. Now, unfortunately, not all Drinfeld modular forms have A-expansions. Well, for one thing, we have Drinfeld modular forms that have more interesting eigensystems than just p to the n. And for another, even if I require that, even if I ask the question, do all eigenforms with eigensystem p to the n for some n have an A-expansion, even then, unfortunately, the answer is no. So I computed this for my thesis. So if you look at h squared times g squared, this turns out to be an eigenform for dimensional reasons, because this is a double cuspidal form, and then the space in that weight is dimension 1. It has an eigensystem which starts with p to the 4. Okay, so I should have said this before. Even if you have an eigenform, it's difficult to compute the eigensystem. Okay, so even the fact that we know eigensystems is a good thing. So I was able to compute for all primes of degree less than or equal to 4 that the eigenvalue is p to the 4, and unfortunately it turns out that this h squared times g h squared g squared doesn't have an expansion. Okay, but let me tell you about the good things. So these are the bad things. Not all forms look like this. Oh, the good things is that we have some applications like congruences. Okay. Now, if you look at these, I'm just gonna sort of walk you through how you prove the first congruence, and it's really trivial, right? You just look at the coefficients, okay? Because these guys, they match, because a to the q cubed minus a to the q is divisible by, oh, by the way, I should have said this. Here's some notation. I is t to the q I minus t. Right? So this is obvious from the A expansion. On the other hand, this is h, and this is calculated to be this. Now it seems to me at least difficult to show without the middle step that h has to be congruent to this modulo bracket 2 to the q. Okay, and here's another example underneath. And I have a theorem in my paper, but I just wanted to give a couple of examples. Okay. So again, it's not obvious how to show these without the A-expansions. We have non-trivial representations of eigenforms as products of eigenforms. Okay. Now this classically doesn't happen very often. Okay, but in this case it happens more often than you would think. And what do I mean non-trivial? Well, look, we're in characteristic P. So if I have an eigenform, I can always raise it to the p power. Yes, or to the q power, and then I get a new eigenform. So forget about these. I'll say that these are trivial. Now these are different, right? So for h, this comes back to Geckler's question. For h, if it seems that if I take h to the j power, then I always get back my A expansion, and I get some other examples as well. Okay. Now I am not. I don't have a proof about this. I have a conjecture, and one of the requirements for the conjecture is that the product of Gauss polynomials has to match. So, for example, in the second example, g sub 7 times g sub 8 has to be g15. Okay, and even then, I mean, I don't even know for which values this happens in general. Okay, but you get some examples. What else? Another important congruence is that E, which is the form written on the left, is congruent to H mod T. Okay, and this, I don't know if I'll have time. At the end, you can either ask me, or if I have time, I'll do it on the board. I'll show you how this easily shows that the Hecke action mod T is never nilpotent. Okay? Now this is very different from the classical case, right? Because the Hecke action mod 2 is always nilpotent. This was, I think it was conjectured by Serre or observed by Serre, and then Tate proved this. Okay, so this is another good application. And the last application that I'll mention is you can actually see that the space of single cuspidal modulo double cuspidal modular forms for GO2, gamma 1 T and gamma naught T is generated by eigenforms with eigensystems P. Okay, and gamma 1 T, this case, is done with a completely different technique by Boyko. And to me, it's interesting to see how was the connection between the two techniques. I mean, his technique is cohomological. Mine is sort of, we have these nice A expansions. Okay, and maybe I should just write down one family related to this to show you why this is the case for GO2. So for GO2, we have an important special family, as I call it, of type 1 forms. So S is bigger than or equal to 1, and then F sub S is the sum over the monics of A to the 1 plus S times Q minus 1 UA. Okay, so this is the coefficient, this is the U sub A. This is always, this satisfies my theorem all the time for all S. And this is in S2 plus Q minus 1, 1, but is not double cuspidal. And it has the correct eigensystem. And basically, how do you get the results for gamma 1 and gamma naught? You induce forms from GO2 upwards. You multiply Z by T. Okay. All right. So I think this is all I want to say about Drinfeld modular forms and A expansions. Any questions? No. Well, let's think big. Let's think about bigger spaces, right? So you may wanna include the space of Drinfeld modular forms into the space of Drinfeld quasi-modular forms. Okay, so here you again have weight and type, and you have depth, and depth is with respect to this false Eisenstein series of weight 2 and type 1, which was discovered by Geckler in 1988, or at least that's when his paper is from. And it turns out that in this case, what is the good thing about these guys is you can use divided derivatives. So I've written down all the definitions. I'm not going to tell you the definition, it's on the board, but what I will tell you is that divided derivatives respect A expansions. So as you can see this last line, see if you use one of those divided derivatives on A expansion, you basically get the A expansion for n plus nu, and then Ca a to the nu, and this is a constant that you can compute. Okay. So the divided derivatives preserve the space, and they also preserve A expansions, and then you already know a bunch of examples, right? You know E, and you have the Drinfeld modular forms that's from my theorem, so you can use divided derivatives on those and still stay in the space. And it seems that this is everything that you get. I mean, at least computationally, it seems that this is all you get. There are no more examples. So if you apply divided derivatives to E and the forms we already have, that's the case. Now this brings us back to my theorem. Maybe the real reason is that you have this nice family, and then you apply divided derivatives, and the times when the divided derivative still gives you a modular form is exactly the things that you get from my theorem. That may also be happening. So maybe this is more important than the big F sub kn, this special family. Okay, well, let's think even bigger. Okay, so Bosse and Pellerin consider the space of deformations of quasi-modular forms. So what is the deformation of a quasi-modular form? Well, we're going to take a new variable, little t, and the deformation of a quasi-modular form is going to be a function in z and t, and this is which looks like a double power series in little t and little u. Okay, and it's going to have modular properties, which I'm going to list in a minute. Now, why is this better than the previous space? Well, because it connects with Anderson generating functions. So what are those? Let's pick a lattice lambda and omega, an element in the lattice, and let's consider the power series in little t, which is defined by this formula. These guys play a role in the uniformizations of t motives. And if I call S sub 2 the Anderson generating function for which I take the lattice to be this. So this is a two-dimensional lattice. Z is in the upper half plane. All right. So this, if I take S sub 2 to be the Anderson generating function for this lattice, and with the Z, it turns out that S sub 2 is one of these things. Okay, and you may be confused by now. What am I talking about? So. Well, I have another slide. I was going to say here are the modular properties, but we have to wait for one more slide. So let's say that S sub 1 is going to be almost the same as S sub 2, but I'm going to take 1 as my element in the lattice. And S sub Karlitz is going to be, again, one of those Anderson generating functions. And let's normalize S sub 1 and S sub 2. So S sub 1 and S sub 2 are the things that matter, and D1 and D2 are normalizations of them. And I just want to make one thing clear, because I gave this talk before and people were confused. So from now on, there's no more derivatives. Okay, so D1 and D2 are not derivatives. Okay, they're functions in Z and T. Okay, because at the end of the last talk, people were asking me, so D1, D2, what are those derivatives? So no, these are functions. Okay, now one can compute the D2 when you apply gamma to Z inside its variable, transforms like this. So look what's happening here. We have the usual factor of automorphy here. Here you have something different. You have D1 over D2, and it looks like the factor of automorphy, except instead of capital T, you've plugged in little t. Okay, and then here's D2. And this is precisely what deformations of quasi-modular forms look like. So you introduce a new factor of automorphy, this block J here. You also introduce this new factor block L, which corresponds to the quasi-modularity, and you look for functions that satisfy this rule. Okay, so you in some sense break up the weight. So the weight was previously K, now it's broken up into mu and nu. Okay, and you also break up L. And why are these called deformations? Because if you plug in capital T for little t, you get quasi-modular form of weight mu plus nu type m and depth L. And this is all done by Pellerin. So this is, none of this is my work. Okay, well, here are some examples. If I multiply d2 by h, it's an example. It has this transformation property that I've stated. We also have a block E, which has the following property over there. Now, why these block this, block that? Because if you plug in capital T for little t, you get exactly little h and little e. Okay. Now, what really interested me is the fact that Pellerin in 2011 actually proved that block E also has an A expansion. Okay. Now, this is different than before, right? Because I've put this bar. And remember, the bar means that instead of capital T, I have little t inside. Okay? So, he has proved this result. Well, then it's natural to ask whether capital H has an A expansion. Well, computationally it does. So this means this appears to be true, but I cannot prove it yet. Okay? Now look what's happening here. Before, for little h, we had a to the q. It's like I've taken out part of this and I've plugged in little t, and I have a to the q minus 1. Well then, of course, we should keep asking questions if we cannot answer them, right? Oh, go ahead.
May I ask a question?
Yeah, go.
Computationally, it seems true.
So both of these have U expansions, so I calculate the U expansions up until some degree.
How many?
The first 100, I think, coefficients.
For small q's?
For small q's, yeah. Q, 2, 3, 4, 5. Yes. So remember, capital H is d2 times little h, so little h I can compute. d2 also has a U expansion, so I can compute this, and then I multiply them together and I see whether it matches this. So we should keep asking questions, right? So we have this nice little family, f sub s, okay? Well, I should probably multiply this by d2 and call this block f sub s, and I should ask whether this has an A expansion.
So have you computed it?
Yes. So the answer is yes sometimes. Okay? So the answer is yes for these values of s. Okay. Now there is a pattern in this, which I haven't written down yet, but there is definitely a pattern. I mean, if you can see, you first get the powers up until q, and then for the next thing, well, you take 3 and you add 2 and you get 5, and you get 3 and you add 3 and you get 6, and do it so on, right? And then here 9, well, I should probably add 5 to it to get 14, and I should add 6 to get 15, so on. Okay? So there is a pattern. I haven't written it yet. It's not for all s, but for some s. Yeah, and as I said, I've checked that the U expansions on both sides agree. Well, why stop there, right? So maybe we can multiply by a square and break off a better chunk of the A expansion. And again, it seems that the answer is yes sometimes. Okay, here I don't really know what the pattern is, but yes, for some s. Okay, so maybe I should stop here. So this is everything that I did numerically. Okay, now you can say, well, this is one direction. Maybe you should also think about powers of block E, right? It seems that always if you raise to j and j is less than q, something should work. And this is a conjecture that me and my collaborator from Texas A&M, Professor Ogindi, have been working on, and we thought we had the second case about a month ago, and we almost sent it out to a journal, and then we found a little mistake, so this is still work in progress. So this is some sort of a product equal to an A expansion type of result, right? Because for block E we already have an A expansion, and this just says we can compute the j and the sum. Okay, and here's my question for you. So it seems that if you can prove the following claim, which I've checked on a computer for some n, and it seems to work, it seems that this is the key to our conjecture right now. So look what's happening here. X and y are two new variables. Again, we keep the capital T and the little t. And A sub n is the primes of degree less than n. Not the primes, all the elements of degree less than n. So it's this nice vector space. Is it true that we can commute the j in this formula? Okay. So if anybody has any idea about this, I'm happy to talk to you. Or if you have an idea, you can write this as a preprint and put it on the archive so I can reference it. Or tell me about it and I'll give you credit. Okay, but if anybody has an idea about this, please tell me. It seems that this is one of those things that people like Karlitz should have done, and probably they did, but I just don't know how. And this looks a bit scary right now, but let me say a few more things about it. So this is a rational function x and y. However, the denominators match. So really you're looking at the numerators, right? Because the denominators are the same thing. And in fact, if you take x to be y to the q, and the variable on the top is little t, is capital T. I mean, I've hidden it into a and b. But if you also take t to be t to the q, you immediately get that the two things are 0. Okay, so this is by a computation that you can do, and this means that the actual numerators share a irreducible. Okay, but beyond that, I don't know what's happening. Again, if you have some ideas about this, I'm really interested in learning about this. Okay, so maybe I should tell you about vectorial modular forms as well, because this was in the title and it has to be in the talk as well. So let's look at representations from GL2 of A to GLS of FQ Laurent series in T, little t. Okay, the following is definition due to Pellerin. So deformation of vectorial modular form of weight W, dimension S, type M, radius R, associated with rho is the following sort of thing. It's a vector F such that it transforms like so under gamma. Okay, so here you have the usual factor of automorphy, you have the determinant, and then you have rho. Okay, and I should give you an example to show where he got, I think that's where he got his first example from. So if you consider D1 and D2, remember those D1 and D2 that I've defined, this is the way that they behave. And there are more examples that Pellerin has obtained. Now, using these, and if the claim is correct, this is also going to be an example of a deformation of vectorial modular form, and then you can use some linear algebra and show the claim that I have, or me and my collaborator have. Okay, so I know this is a bit vague, but this is maybe something that I would like to call an A-expansion of a Drinfeld vectorial modular form. So as you can see here, you have the usual factor of automorphy, and this seems like something that should be the deformation of that. Okay, and I think this is my talk. Do I have more time or no? No, I don't think so. So, thank you.